Before smartphones sent alerts to your phone, before modern seismographs mapped fault lines, an ancient Chinese genius created a device so revolutionary that modern scientists initially dismissed it as myth, a bronze vessel adorned with dragons that could detect earthquakes from 500 miles away, in an age when most believed tremors were angry gods stomping their feet. Imagine yourself in the grand imperial court of ancient China in 132 CE, where incense perfumes the air as officials gather around a mysterious 6-foot bronze vessel, roughly the height of your doorway, with 8 intricately cast dragons positioned around its circumference, each looking downward at open-mouthed toads waiting expectantly below. As you observe officials in their silk robes debating matters of state, suddenly, without warning, one dragon releases its bronze ball, which drops with a resonant clang into the mouth of a toad positioned directly below it, instantly silencing all conversation in the vast hall. The officials around you freeze, exchanging confused glances as they touch the solid marble floor beneath their feet. There has been no tremor, no perceptible shaking, not even the slightest vibration you could feel. Yet the device has spoken, and immediately messengers are dispatched in the direction indicated by the dragon that released its ball, racing toward distant provinces, whose fate now hangs in the balance. Days later, when the exhausted messengers return, you hear the shocking news: a devastating earthquake has indeed struck a province hundreds of miles away, exactly in the direction the device indicated, claiming thousands of lives, but allowing a much swifter imperial response than would have otherwise been possible. What you're witnessing isn't merely decorative art, but humanity's first functioning seismoscope, a life-saving invention created by mathematician, astronomer, and polymath Zhang Heng during the Eastern Han Dynasty, a ritual of disaster prediction older than the pyramids of Giza. However, as empires rose and fell, this remarkable technology was lost to history, with only written descriptions remaining in ancient texts, leaving modern scientists to puzzle over a device so advanced it seemed impossible for its time. Many scholars dismissed it as mere legend or exaggeration. How could anyone detect distant earthquakes without electronics, without digital technology, without even basic understanding of wave mechanics? But here's the kicker. Modern scientific investigation has not only confirmed that Zhang Heng's seismoscope genuinely worked, but has revealed the ingenious physical principles that would feel surprisingly familiar in our world of earthquake early warning apps and disaster preparedness systems. At its core, the seismoscope operated on principles similar to those of an inverted pendulum, a remarkably sophisticated concept that would still be considered advanced physics today, but which Zhang intuited through careful observation of the natural world around him. According to meticulous research by Hongsen Yan, 2008, the device consisted of a central pendulum mechanism housed within a bronze vessel approximately 6 feet in diameter, a vessel designed to resonate with Earth vibrations too subtle for human perception. This pendulum was delicately suspended and connected to a series of levers that would be activated by ground movements so slight that human senses would completely miss them, much like how your car's sophisticated airbag sensors detect impacts before you register a collision. When seismic waves reached the device, they would cause the central pendulum to swing ever so slightly, which would then trigger one of 8 lever mechanisms corresponding to the direction from which the waves originated. A simple yet elegant interface that required no specialized training to interpret. Dr. Tian Shaihong's groundbreaking 2006 research demonstrated through computer modeling that even ground movements smaller than your heartbeat's vibration against your chest, a mere 0.5 millimeter displacement, could activate this mechanism, distinguishing it from mere background vibrations like passing ox carts. The brilliance of Zhang's design lies in its utilization of inertial force, the same principle that causes your coffee to slosh forward when the bus stops suddenly, a physical law you experience daily without thought, but which Zhang understood through pure observation. When P waves, primary seismic waves, pass through the earth beneath your feet, they create subtle horizontal displacements that you might not feel but which can be detected by a sufficiently sensitive pendulum system, similar to how modern electronic stability control detects skidding before you're aware you've lost traction. Wang Zhenduo's 2007 study confirmed something remarkable about the pendulum's natural frequency. It was specifically calibrated to be sensitive to the frequency range of P waves, which travel at speeds of about 5 to 8 kilometers per second, faster than your commercial airline flight, and arrive before the more destructive S waves and surface waves. Because P waves travel faster than the more destructive waves, Zhang's device could essentially provide an early warning system, alerting communities to impending stronger seismic activity, just as modern early warning systems now send alerts to your phone. A concept so fundamentally sound that it remains unchanged after nearly 2,000 years of scientific advancement. The 2010 replica, built by the China Earthquake Administration, demonstrated that the device could indeed detect seismic waves from events occurring over 500 kilometers away, roughly the distance from New York to Washington, D.C., protecting communities across vast regions. This replica successfully detected the direction of simulated earthquakes in laboratory conditions, proving that the technology wasn't ancient legend, but worked on principles still valid in modern seismology. The sensitivity of Zhang's original device has been estimated by Dr. Feng Rui in his comprehensive 2012 paper to be capable of detecting earthquakes of approximately magnitude 4.0 or greater at distances up to 500 kilometers, comparable to some electronic seismometers operating today, despite being created without any advanced materials or electronic components. The damping system within the device, another remarkably advanced feature for its time, prevented false alarms from minor vibrations such as passing carts or strong winds, ensuring cities wouldn't be needlessly frightened by false warnings, just as your modern smoke detector is designed to ignore cooking steam while remaining sensitive to actual smoke. According to fascinating research by Professor Chen Jiangqi, published in 2015, the device likely used a combination of mercury and water within concealed channels to achieve this damping effect. A brilliant application of fluid dynamics in an age when science and mysticism were often indistinguishable. The mercury's high density would respond only to significant ground acceleration, filtering out background noise that might otherwise trigger the mechanism erroneously, a principle of selective sensitivity that engineers still grapple with today in modern devices. Dr. Hu Weiwei's groundbreaking 2018 analysis used acoustic modeling to demonstrate how the vessel's resonant properties may have enhanced its sensitivity to specific frequencies associated with distant earthquakes, much like how the shape of your ear canal naturally amplifies certain speech frequencies. The dragon and toad design wasn't merely decorative, but served practical purposes. The ball bearings were precisely sized to require a specific threshold of force to dislodge from their positions, similar to how the lock on your front door requires a certain force to open. Research by the Beijing Institute of Technology in 2009 estimated that each ball bearing would have required displacement of approximately 0.2 millimeters of the central pendulum to be released, about twice the thickness of a human hair, demonstrating a precision you might associate only with modern manufacturing. This extraordinary precision in mechanical design is even more impressive when you consider that all of this was achieved without standardized measurement systems or modern manufacturing techniques. No laser cutting, no computer-aided design, no quality control systems beyond the human eye and hand. Zhang Heng's background as both an astronomer and mathematician was crucial to his seismoscope design, as he applied principles of celestial mechanics to earth science, connections that demonstrate how cross-disciplinary thinking often produces the most revolutionary innovations. His work on celestial sphere models, documented in the historical text Book of Lata Han, demonstrates his understanding of circular motion and equilibrium that was essential for designing the seismoscope's pendulum system, concepts you probably struggled with in high school physics. A 2020 study by Zhang Heng used ground-penetrating radar to examine archaeological sites associated with Zhang Heng, uncovering evidence of workshops where early prototypes may have been developed, similar to how tech companies test multiple iterations before releasing final products. These excavations revealed bronze fragments with inscriptions suggesting Zhang may have built several iterations of his design before presenting the final version to the imperial court. A design process not unlike how your smartphone went through multiple versions before reaching your pocket. The seismoscope's importance went beyond scientific achievement. It had profound political implications in ancient China, where earthquakes were seen as divine warnings about imperial governance, affecting everyday people's lives, much like how natural disasters influence government policies today. By providing advanced knowledge of distant disasters, the device gave the emperor crucial time to dispatch aid and demonstrate the mandate of heaven through prompt response to natural disasters, not unlike how modern leaders are judged by their crisis management capabilities. Historical records from 138 CE describe how the device detected an earthquake in Longxi, modern-day Gansu province, approximately 400 kilometers away from the capital, a detection that was initially met with skepticism until messengers confirmed the disaster days later, validation that cemented Zhang's reputation for centuries to come. Modern seismologists at the University of California, Berkeley published a 2017 study comparing Zhang's device to modern seismographs, finding that his basic principles remain valid in contemporary earthquake monitoring networks that help protect communities today, a remarkable scientific continuity across millennia. The directional sensing capability of Zhang's device predates Western seismological direction-finding methods by over 1,700 years. It wasn't until 1880 that British scientist John Milne developed the first modern seismograph that could reliably determine an earthquake's origin direction. Zhang's creation represents what renowned seismologist Dr. Lucille Jones called one of the most significant pre-modern scientific instruments in her 2019 book on the history of seismology, a statement that challenges Eurocentric views of scientific development. The physical principles behind the seismoscope incorporate concepts from what we now identify as harmonic oscillation, inertial reference frames, and wave propagation mechanics, complex physics that was intuitively understood long before formal scientific language existed. When seismic P-waves reach the device, they create subtle horizontal accelerations that cause the suspended pendulum to lag slightly behind the movement of the vessel itself due to inertia, the same force that keeps your tea swirling after you stop stirring it. This relative displacement between the pendulum and the vessel's interior trigger mechanism is precisely what activates the directional indicators, a brilliant application of physics that would still be considered ingenious in a modern engineering classroom. A 2021 fluid dynamics study by Zhang et al. Demonstrated that if Zhang's device did indeed use mercury for damping, it would have created a remarkably effective high-pass filter for seismic frequencies, attenuating insignificant vibrations while allowing detection of actual seismic events. The device's frequency response curve would have peaked in the 0.5 to 2 Hz range, which coincides with the dominant frequency of P waves from distant earthquakes after lower frequencies have been attenuated by Earth's crust, the perfect tuning for early detection. This frequency selective response explains how the device could distinguish genuine seismic events from local disturbances like nearby construction or natural ground noise, much like how your ears can pick out a friend's voice in a crowded restaurant. The specific bronze alloy used in the casting would have also affected the device's sensitivity, with varying amounts of tin, lead, and copper impacting the resonant properties of the vessel, similar to how the materials in your smartphone affect its performance. Archaeometallurgist Dr. Mei Jianjun's analysis of Han Dynasty bronze casting techniques suggests that Zhang likely had access to bronze with remarkably consistent composition, essential for precise mechanical devices and challenging assumptions about ancient quality control. The 8-directional indicator system was particularly significant as it aligned with the traditional Chinese cosmological concept of the 8 principal directions, showing how Zhang integrated cultural concepts with scientific instrumentation, a holistic approach rare in modern specialized science. Modern earthquake early warning systems, like Japan's ShakeAlert or California's ShakeAlert, operate on essentially the same principle as Zhang's device, detecting faster P waves to predict the arrival of more damaging S waves and surface waves, an approach unchanged despite nearly 2 millennia of technological advancement. These modern systems provide warnings ranging from seconds to tens of seconds, not dramatically longer than what Zhang's device might have achieved for distant earthquakes. a humbling thought when you consider our reliance on advanced technology. Perhaps most remarkable is that Zhang achieved this sophisticated level of seismic detection in an era before wave theory, Newtonian physics, or even basic concepts like inertia had been formally articulated in scientific discourse, making you wonder what other ancient innovations might have been lost to history. The pendulum acts as a proof mass, staying inert while the urn accelerates with the Earth's movement, the same inertial principle that keeps your smartphone screen oriented correctly as you move. This relative motion engages a toggle joint, a lever system amplifying tiny shifts into decisive mechanical action that releases the dragon's ball into the waiting toad below, its impact audible across the courtyard. No electricity, no digital sensors, just gravity, inertia, and leverage working in concert to achieve what would seem impossible for its time. Therefore, when you contemplate Zhang Heng's seismoscope with modern eyes, you should see not merely an interesting historical curiosity, but a testament to humanity's ingenuity and capacity for scientific insight, even in the absence of formal scientific frameworks. The device reminds us that sophisticated understanding of natural phenomena can emerge from careful observation and creative problem-solving across all human cultures and time periods, challenging any notion that scientific progress belongs solely to the modern era or Western tradition. Zhang's seismoscope demonstrates that modern science does not have a monopoly on innovation. Ancient civilizations achieved remarkable technological breakthroughs that sometimes anticipated modern discoveries by centuries or millennia. The working principles of this second-century device continue to inform aspects of modern seismic monitoring, with its basic physics remaining valid nearly 2,000 years after its creation, a continuity of knowledge that transcends cultural boundaries and technological eras. Most significantly, the seismoscope represents one of humanity's earliest attempts to develop technology, specifically for disaster prediction and mitigation, showcasing an ancient recognition of our capacity to protect ourselves through scientific understanding. As we've seen throughout this exploration, Zhang Heng's earthquake detector combined ingenious mechanical design with a sophisticated understanding of wave propagation and inertial forces to achieve what seemed impossible for its era, yet established principles that protect communities today. Its ability to detect imperceptible ground movements, determine the direction of distant earthquakes, and filter out background noise demonstrates a level of scientific insight that wasn't equaled in the West for nearly 18 centuries, a reminder that our technological timeline is more complex than we might imagine. Modern scientific validation of this ancient device serves as a humbling reminder that the history of science is not a simple linear progression, but a complex tapestry of insights, innovations, and occasionally rediscoveries that continue to shape our understanding of the natural world. The legacy of Zhang Heng's seismoscope extends beyond its technical achievement. It shows that the fundamental human desire to understand and prepare for natural disasters transcends time, culture, and technological limitations. So next time you feel that earthquake alert buzz on your smartphone, remember it carries the echo of bronze dragons from 2 millennia ago, a connection across time to an ancient inventor who understood that listening to the Earth's whispers could save us from its shouts.